Okay, so here's a problem where we need to find the internal shear force and bending moment as a function of x. And I've defined x here. Unless otherwise described, I'm always going to assume that x goes in the traditional sense from left to right, from the far left edge to the right, which is kind of our standard convention. There will be some problems where it would be a lot easier if you restart your x value at different origins across the beam. We'll talk about those as they come up. But for now, I think this one will work fine. So we probably should first think about how we want to solve this problem. So if we're going to solve for the shear force and bending moment at x, and you can see I've already just given an arbitrary value of x, I'll go ahead and imagine a cut there. And now you need to decide whether you want to work the left side or the right side. If I did want to work the right side, what would this length be here? 20 minus x. So it's still a function of x. Now, is there any advantage of working the right-hand side?
No reactions.
No reactions. However, what does my loading look like? It's a trapezoid, and from our previous work, we know that they can be a little more challenging to deal with. You probably break it up into a rectangular section and a triangular section. So compare that to the left-hand side. What do you have? Well, the load is simply a triangle, so that's just one thing to keep up with. It's also going to be a function of just x, where all these values over here are going to be functions of what? 20 minus x. So your function could be a little less tidy, let's say. So I think for just finding the reactions here, that's a simple amount to pay to be able to just do everything in terms of x. So you can go either way, but I think today, just to get started, we're going to go left. So since I'm going to go left, I'm going to need my reactions. So I'm going to draw another free body diagram of this structure. And the first thing I'm going to do is find a concentrated equivalent of the entire load. So it's a triangle. So we know the area of a triangle is 1/2 the base times the height. When you do that calculation, it looks like you're going to get 20 kips. And where would that be located? About right here. And what's that distance from the cut? It would be 2/3 of 20, right? Just because I don't want to carry around a fraction right now, I'm just going to write that as 40/3 feet. 2/3 of 20. Okay? Now I'm going to assume directions for my shear force and bending moment here at the end. Not just a force and not just a moment, but shear force and bending moment. So on this left edge, positive shear force is up or down? It is. It's 50-50. I hear both. Let's vote. All for up, raise your right hand. That's not a majority. That's unfortunate. It's up. Why is it up?
Because the beam, it always makes a smiley face.
It's trying to rotate the beam clockwise. Right? What about bending moment? I think that's easier. Is it going to be clockwise or counterclockwise on that left edge? Clockwise. So there's positive bending moment and positive shear force. I'm going to find those two. How do I do that easily? What's the easiest thing to do first? Sum moments where? At A. So I'm going to assume right-hand rule for my sign convention. Now I'm back to statics, so I can do what I want in terms of sign convention. So in terms of statics, with this sign convention, what kind of moment is that? Negative. What kind of moment about A does this 20 kip force create? Positive or negative? Negative. So it has a 20 kip force times a 40/3 foot moment arm. So it looks like my moment is going to be negative. I don't know what that is. That's 800 divided by 3. That's 266.7. Is that right? And that would be kip feet. So what does that tell me? What's my bending moment at A? Negative 266.7. So my equation better predict at x equals 0 a bending moment of negative 266.7. We know that. What about the shear force? Well, it's some forces in the y direction. I'm going to assume up is positive. So this force is up, shear. This force is down, 20. So my shear is equal to 20. So I have positive shear at A. In fact, let me go back and actually subscript those A, because those are the values at A. Because later I'm just going to use M and V as my equations, the variable for my equation. Everybody good with that? So now I'm going to draw a free body diagram of this left-hand side. I'll draw it a little bit larger so we can see it. So here's the section. It's of length X. I've got my shear force, which is up, a value of 20 kips. And my bending moment now is negative of 266.7 kip feet. And then I've got my loading, which is triangular. Oh, by the way, what's the intensity of that load right there? Does it vary?
Yes, it does.
Yeah, so it's going to be a function of x. So what is that function of x?
2.
What's the slope of that line? Rise over run.
1 to 10.
1 to 10. So it should be x over 10. And that should have the units of kips per foot. Now, does that work? When x is 0, what does this equation predict the load is?
0.
And x equals 0 it is. When x is 20, my equation predicts it should be 20 divided by 10, which is 2. So it works. So far, so good? Okay, so now I'm going to come in here and I'm going to assume positive shear and positive bending. What's positive shear on the right-hand face? Up or down? Down. Why is it down?
Because it's 10 clockwise.
Well, that piece under that force would rotate clockwise. And then, of course, we want it to be happy, so we put on positive bending moment, which would bend it into a nice happy face. Right? How many unknowns do we have? 2. Shear and moment. Now, I don't want to deal with the distributed load, so I'm going to deal with the concentrated equivalent force. I'll just call it F. And what is F? It's a triangle. Triangle is what? 1/2 base times height. So 1/2 base. What's my base? X. What's my height? X over 10. So that ends up being x squared over 20. And what's the distance from this cut face? I'll call it D. What's that distance, D? It's the length divided by 3, which is x over 3. That's the hardest part to these problems, is drawing the free body diagram, breaking all the components down. At this point, it's just equilibrium. Mr. Rippey.
I'm hung back at the sum moments around A. Should that be 20 over 3 or why do we put 40?
It wouldn't be 20 over 3 because 20 over 3 would be this distance. I want the distance from A to the centroid. It should be 2/3 of 20. So 2/3 of 20 is 20 divided by 2/3. That's 40 over 3.
Yeah, I got it.
I I just didn't want to write it out as 13 point something something. I just left it like that. Okay, so now what we're going to do is make sure this is in equilibrium, so I'm going to come and do that. So I'm going to sum my moments at the cut, right, method of sections. And I'm using right-hand rule for my sign convention. So starting on the left, this moment is what? Positive or negative?
Negative.
Positive.
How about positive? Yes.
About the cut face, this force F is going to create positive or negative moment?
Negative.
Positive. Positive. Right-hand rule. Right? This is the cut face right here.
Okay, I was looking at it.
You're doing about A.
Yeah.
So that's going to be positive the force, which is x squared over 20, times the distance, which is x over 3. So remember, there's the force, there's the distance. Now I go over to this 20 force, which is my reaction. What kind of moment does it create about the cut? Positive or negative? That one's negative. So that's going to be 20. And what's the distance? X. And then I get all the way over here to this moment. What kind of moment is that with right-hand rule? Positive or negative? Positive. So I'm going to solve for my moment. So you can see when I solve for my moment, it's going to be a function of x. So I'll throw everything to the other side of the equation. I'll also bracket it so I can put my units on it. So I'm going to have negative x cubed over 60 plus 20x minus 266.7. And all those terms will have the units of kip and feet. So I now have an equation for my moment anywhere in the beam. Where are the two places I know my moment? What's the moment at A? The bending moment at A. We solved for it. And that's at what value for x? 0. So if I plug in x equals 0, what do I get? Negative 266.7. It works. Where else do I know my moment? Well, I know I have an equation for it at a cut, but where else do I know it as a value? B. What's the value at B? 0. So I put in x equal 20 here. I better get 0. Why don't you guys check that real quick? I'm going to go ahead and write here that at the moment at x equals 0 does equal to 66.7, and that's kip feet. Kind of ran out of space there. Sorry about that. And also the moment at x equal 20, I think it should be 0. Is it? Anybody run those numbers yet? It's okay? So I'll say, check. I got those. So far, so good. Now what do I do? What have I not checked for equilibrium? Well, I don't know my shear. So let's come back now and sum forces in the y direction to make sure that's in equilibrium. So I'm assuming up is positive, so my shear is down. My force is down, and that force is x squared over 20. And my 20 kip force is up. That's it. So solve for my shear. It looks like my shear as a function of x is minus x squared over 20 plus 20, and that should have the units of kips. Now, does it match what I know? Well, we solved for the shear at 0. What was it? 20. Does my equation give me that? Yeah, you put in x equals 0, you get 20. What's the shear at the free end? X equal 20. Should be 0. You put in x equal 20 here, you get 0. I can see that. So again, check. Now, thinking about your walk across campus to Dunn Hall and all the pleasures that you get there, do you see any relationship between these two? Mr. Maxey is bobbing his head like the little dogs in the back of the car. Yeah. I hear some low rider music coming on. Okay, so what else? Anybody else see it? What is it? It's the derivative. It looks like the derivative of the moment with respect to x is equal to the shear. That is pure anecdotal. I'm just looking at it. That may not be the relationship, but I can tell you it is. And we'll prove it later, but that's a nice little thing to know, because if you get your moment equation and you take the derivative, we always have nice polynomials, so they're easy to take the derivative. So if you take the derivative and you don't get the shear, something is not right. Either your shear is wrong or your moment's wrong. And since the moment equation tends to be the more complicated one than the shear equation, more than likely your moment is wrong and your shear is right. So these are problems where you get all kinds of feedback whether you're doing it right. So I'm expecting you to do it right and not do it wrong. How many of you want to participate in that policy? Raise your right hand. Excellent. Almost everyone raised their right hand. Some of you do not want to participate. That's fine. Oh, Mr. Birmingham finally jumped in. Okay, now we're all in. It's unanimous. So keep that in mind. You've got checks at places. Sometimes you do know these, sometimes you don't. But you also have this relationship. So there's a lot of ways to check your work. Now, just as an example, where's the maximum moment and where's the maximum shear? We kind of already know that. You could simply just plot this equation and see where it has the maximum value. And the same with this one. But we already know that in a cantilever structure, they both occur at the fixed connection. Now, when we do a simple supported structure, it gets a little more challenging. But you don't know necessarily where those happen. So any other questions before this one, before I turn it off? Okay.